Hello ladies and gentlemen, and welcome to part 4 of the pre-course preparation on quantitative methods pack. As with all the other parts, the aim of these notes and this recording and the exercises is to allow you to practice topics that you either know or you might not know, but you either know and haven't been exposed to for a while, or you don't know at all. And for this particular part, for part 4, we can break it into 2 sections. Firstly, we're going to discuss something that is called inference statistics. And what inference statistics allow us to do is to use data that we collect about the past and infer about the future. And by inferring, we are going to forecast the future. So we're going to use tools like estimation, hypothesis testing, correlation and regression, and we're going to do that to develop a forecast, to develop a model, to develop a way in which we are able to forecast the future. And by forecasting the future, by having that model, we are able to then say, if we do this, what do we expect will happen? Or if we want this outcome, what decision do I need to make now? What do I need to do now? So that's inference statistics, and that's the first part of what we're going to do today. The second part, I'm going to summarize it. I know there are 2 words in there, but I'm going to summarize it into optimization. So we're going to use tools like simulation. We're going to use tools like linear programming. We're going to use tools to simulate the future, to develop a model, but in this case, unlike the first one, we're going to insert uncertainty into our model. And we're going to not try to find an outcome, but to try to identify, in a lot of instances, what is the best outcome. And thus the name optimization. So we'll get through all of that in this next hour or hour and a half. And then, as always, you're going to have some exercises that you can use for practice, and you're going to have the references at the end of these notes that you can look for and look at these topics in more detail. So, as always, use these notes if you've never heard of these topics. Very useful. Or if you have heard of these topics, but have studied in a different language, or haven't studied for a while, and so you want to get comfortable with the terminology. As always, these topics over the course of your degree, they're going to be used in different modules. So be aware of it, and as you study those modules, if you ever need, come back and use these materials as a reference. Well, so this is part 4, simulation and optimization, and forecasting as well. We've covered parts 1, 2, and 3, key mathematical concepts, data exploration, probability and probability distributions, and there'll also be at part 5 on financial mathematics. As always, you have these notes, you have this recording, and then there'll be some exercise and respective solutions and the references at the end of this. So without further ado, let's have a look first at forecasting. Now, forecasting, as I said, we are inferring. We are going to use data that we have and build some form of model to forecast what's going to happen in the future. The simplest of these tools is a tool called estimation. In estimation, what we have is we take a sample. Now, when I say we take a sample, it doesn't mean we have to go and take it. We may have it by nature. So as we run our business, we keep records of how many units of each product we sell, of the price we charge for our products. So we don't need to go and do anything other than use the data that we already have. But that data is a sample, because there will be more periods in the future, because we may not have data for 30, 40, 50 years ago, or we may have but consider it not to be significant because the business environment was very different, whatever it is, but we're going to use a sample of data. And for that sample, we're going to calculate sample statistics. And in that circle on the left, we have some sample statistics and the notation that I used. So we use X bar to represent the mean of a sample. We use S square to represent the variance of a sample. Just S would be the standard deviation of the sample, and we use small p to represent the proportion of the sample. So proportion we use when we are looking at how often something occurs. So for example, if we have an election and there are 4 parties running for that election, and we ask people to vote, even if we call them parties 1, 2, 3, and 4, it makes no sense to take the answers from our sample and say that on average they're going to vote on party 2.3, because that makes no sense. There doesn't exist a party 2.3. So what we're going to do is take the number of responses we have and calculate what proportion of the sample has indicated that they would vote for party 1, 2, 3, or 4. So that's the proportion from a sample. Once we've calculated those statistics for the sample, we now are ready to estimate what are the true values for those same statistics for the population. And so where we have X bar, which is the mean for a sample, mu represents the mean of a population, the true mean of the population. Where we have S square, we've got for the sample variance, we have sigma square for the population variance. Where we have P for the sample proportion, we have pi for the population proportion. Now, important thing to notice here. We know the statistics for the sample, but we do not know the statistics for the population. If we knew the statistics for the population, then there's no more work to be done because we know it. But the reality is we don't, as a rule. We don't know on average how much each one of our customers spends in our store. But we know for the whole population. But we know based on the last months or in the last year what the average spend for that period was. So we know for the sample, the last months all the customers that walked into our store on average spent this much, but we don't know for the whole population, because the whole population is all the customers we ever have and all the customers we will have in the future. So that's, although a mean exists, we don't know it. So what we're going to do is use the sample statistics to estimate the population statistics. Next, we can do something a little bit more advanced, which is not very different, to be honest. And that's something a little bit more advanced is, instead of estimation, we do hypothesis testing. What is the same between estimation and hypothesis testing? The formulations. We use exactly the same formulations, same formulas. What is the difference? The difference is, in estimation, I'm just saying, I'm going to take a sample, find out what the statistics are, and from there, estimate for the population. With hypothesis testing, there's a step before this, and there's a step after this. So, estimation, take a sample, calculate the statistics for the sample, estimate for the population. Hypothesis testing. Before I take the sample, I believe something. I have a hypothesis. So in this example of the average spend, whereas if I'm estimating, I'm just taking a sample. If I'm doing hypothesis testing, I'm starting with, I believe each one of my customers spends on average £122.55 when they come to the store. That's my first step. I have, as it says in there, a claim. Then I do the same as the estimation. I take the sample, I calculate the sample statistics. Based on that, I estimate the population statistics. And then there's one more step at the end. And that step at the end is, based on this estimation I calculated, was my claim correct or not? So, same process, same formulations, because the calculations all come in the middle. One initial step, the claim, the belief I have, the hypothesis I have. One more stage at the end, was I right or was I wrong? Does the data support my claim or does it reject my claim? Now, when setting hypotheses, there's always two hypotheses, and between them, they cover all possible outcomes. One is called the null hypothesis. The other one is the alternative. The alternative is everything that the null is not. The null hypothesis, as the name says, null means nothing, means zero, means no change, means no difference. So the null hypothesis is always either zero or the status quo or no difference, etc. So for example, let's say I've got a factory. I decide to change the layout because I think it will become more productive with a new layout. Now, my hypothesis is obviously that by changing, I'm going to make it better. I'm going to increase productivity. But the null hypothesis is that it will make no difference. The alternative is it will be better. So effectively, the null hypothesis is it will make no difference or it will make it worse. And the alternative is that it will make it better. Then I will collect the data. And in this case, if I run a test, I run a pilot with the new layout to see if the productivity improves or not, and then I collect the data from the test, which is a sample, I would hope to be able to prove that the null hypothesis is wrong, so that I can reject the null hypothesis and accept my claim that the new layout increases productivity. So in a lot of instances, and certainly when we look at regression in a moment, that will certainly be the case, we will be trying to disprove the null hypothesis. Okay? Which is what it says in here. Normally, the claim is in the alternative hypothesis, and I will try to reject the null. So for example, finance manager believes company's productivity is higher than the main competitor's productivity. The null in this case, the null hypothesis would be there is no difference in the productivity of the company and its competitor. The alternative would be, as it says in the second bullet point, a one-tailed test to say that my productivity is higher, is better than the competitor. That is one type of hypothesis testing that we can do, one-tailed test. We can also do a two-tailed test, which is just to say it is different. Okay. Now, here are the formulas, and the formulas are the same. That formula you see in there works for estimation and works for hypothesis testing. Now, estimation, there are two types of estimates that we can make. We can make a point estimate where, for example, we take a sample. The sample mean is 25. So our estimate of the population mean is 25. That's a point estimate, just a value. But the reality is it's highly unlikely that the population true mean is exactly the same as the mean of a sample that we take. Because by nature, a sample does not include every element of the population, and therefore it's not going to be exactly the same. So, to recognize that increased uncertainty that a sample gives us, we can calculate an interval estimate. And an interval estimate we calculate by taking the sample mean plus or minus what's called the margin of error. And the margin of error, depending on what degree of confidence we want, the level, not degree, the level of confidence that we want, will be either narrower or wider. And what that margin of error entails is it has the Z score. If you recall from the previous topic, the Z score is the value that is taken from the normal distribution table. And so, for example, and you can check that with the table, if we want a 95% confidence interval, we want 2.5% on each extreme. So we want 95% in the middle. So we look in the table for the value that gives us, that cuts off the top 2.5% of the distribution. And if you see that in the table, it will be 1.96. So to calculate the interval estimate, we would take the sample mean plus or minus the Z score of 196 times the standard error. And the standard error is the square root of the variance. Because we don't know the population, although it says there sigma, we're going to use S divided by N, which is the sample size. Okay. Now, with hypothesis testing, we can do exactly the same, confidence interval, and then check whether the hypothesized value is included in the interval. We can also do the t-stat calculation for the data and compare with the t-critical. That value I just mentioned of 196 is a t-critical because it is the t or z score that cuts off 2.5%. Or we can also calculate the p-value associated with the t-stat and compare with the significance level that we want. The significance level is 1 minus the confidence level. So if we want a confidence level of 95%, significance level will be 5%. Now, this topic is a topic that has got a lot of detail on it. So I within the time frame and within the aim of these notes, I'm not going to go into all the detail. There's no chance in an hour and a half I'm going to do that. So if you're a total newbie, you've never heard of any of these concepts, I very strongly urge you to look at the references. Some of these, the concepts that I'm mentioning, will make a lot of sense for those who have some awareness of it. For those who don't, it's natural that you're going to struggle to understand what I'm saying. So make sure you use the references, make sure you follow the examples in those books, and then you also be able to make some sense of these. So what I am doing is mentioning key words, key concepts, key formulas, without going through the detail of how we arrive at them. So if you're happy to use those concepts and you're happy to accept them, you should be able to understand and be able to apply these. If you require a little bit more explanation, go to the references. So here's an example in any case of how we do this that will make it a little bit more understandable and a little bit more meaningful. So the example is a company that is interested in assessing, in understanding average spend in store by the customers. That's sort of an example I've used already without a lot of detail. And they take a sample of 50 customers. From that sample, they calculate the statistics, the mean and the variance, which comes out at 78 and 350. And now there's two questions. First part, the estimation part, provide a point and an interval estimate for the population mean. The second part, pretty much the same calculations, but there's that first step, which is the claim. And the claim from the managing director is that they believe that each customer spends an average of £82. So then we do the estimation and we see, can we support that claim or not? This one is not for you to go and do. We're going to go through it now. So first thing, point estimate, very simple, £78. We've got no reason to believe our sample is not accurate, is not representative of the population. And so sample mean was 78, expected population mean 78 as well, or estimated population mean. For the interval estimate, again, a small detail, but quite important in some cases. If we have a small sample, we need to use the t-distribution, which again I briefly introduced to you at the end of topic 3. So have a quick look at that. And if, as is the case here, we've got a sample that is large, over 30, we can use the z-score. We can use the normal distribution table. And so in that case, we take the formula and say 78 is the sample mean, plus or minus the z-score for 95% confidence level, which we saw was 196, I just explained briefly earlier, times the standard error, which is the square root of variance, 350 for the sample, over n, sample size of 50. So that says that I can be 95% confident that the true population mean is somewhere between 72.81 and 83.19, based on the sample I have. Now, if my sample was different, I would come up with a different number. But if my samples were all scientifically collected, what you'll find is that the majority of samples, 95% of samples, will be such that they will include the true population mean. Now, obviously, I may, by chance, have taken a sample of 50 customers who were the ones who spent the least, or taking 50 customers who were the ones who spent the most, in which case this conclusion, this estimation will not be correct. But that's a danger that we can't live without. It's a danger that will always be present. So in this case, to answer part 1, point estimate for the population mean 78. Answer to part 2, on the basis of the sample we collected, sample of size 50 with a mean of 78 and the variance of 350, we can say that we are 95% confident that the true population mean is included in the range 72.81 to 83.19. Now, the second question is about hypothesis testing. So we had the first part where we said the managing director believes that the average spend is 82. So if that's the belief, in that case, because it's an exact number, not more than or at least or anything like that, in this case the claim is actually in the null hypothesis. And the alternative is, doesn't say it's bigger or better or anything, it just says it's 82. So anything outside of 82 would disprove their claim. So what we can do is one of 3 things that we've mentioned earlier. First one, very simple. We have the confidence interval that we calculated in the previous slide. And if you look at that confidence interval, which was from 78, I can't remember anymore, but it was from 75, I think, to 83 point something. 82 was included in that figure. And because 82, not in that figure, sorry, in that range, because 82 is included in that range, that means we can't reject. We cannot say that the mean is not 82, because we said with 95% confidence that the true mean is between, it was 78 minus 5 point something, so 72 point something, and 83 point something. And so in that case, we cannot say with 95% confidence that the mean is different from any of the values within that interval. And so that's the same with 82. The second way to calculate it, as we said, was to calculate the z-score, for the data. And the z-score for the data, we calculate again using the formula for the z-score that we saw in part 3. In this case, hypothesized value is 82, take away the sample mean of 78, and in the formula in part 3, we divided it by the standard deviation. Here, we divide by the standard error, because the sample size makes a difference. And therefore, instead of just dividing by s, we divide by s over the square root of n, or square root of 350 over 150. And that gives us a z-score of 1512. The critical is the same we used before. The z-critical is the 196. And if you recall the shape at the top of the normal distribution table, you will see that it will highlight the extreme of the distribution, is the value that is calculated. So 196 is here, minus 196 is here. So you've got the normal distribution. Those two are the z-critical on a two-tailed hypothesis testing like this one, we've got plus 196 and minus 196. If the Z critical falls within that, between minus 196 and 196, then we cannot reject the null hypothesis, which is the case here. 1.512 is between minus 196 and 196, so we can't reject the null hypothesis. We can also do the same by calculating the p-value. We can do it manually, but we can also use Excel, and that's what I've included in here. We do 1 minus norm dist of 1.52, which is the z-score we just calculated, and then you put 0, 1, and 1, and multiply that by 2. As you open the Excel and you look at the formula, you will see what those different requirements are. Now, don't forget, norm dist uses the standard normal distribution. So 152 is the z-score we just calculated, 0 is the mean, and 1 is the standard deviation or variance, because a normal distribution has got a mean of 0 and a standard deviation of 1. And the final one is to indicate that we want the cumulative value. So because we want the p-value, we want the extreme. So we do 1 minus norm dist of 152, which is the z-score of the data, 0, which is the mean of the standard normal distribution, 1, which is the standard deviation, and 1 for cumulative. And then we multiply by 2 because we want a two-tailed test. Now, this one, if you're less accustomed to do this type of calculations, is obviously the most complex. Have a look. But if we do the confidence interval, or if we do calculation of the z-score, which uses the same formula we've used before, it is a lot simpler. All three methods will lead to the same conclusion. In this case, we've got a p-value of 12.85, and we compare with a significance level of 5%. And because it is more, the p-value of the data is more than 5%, we cannot reject the null hypothesis. And therefore, because we can't reject the null hypothesis, we cannot reject the claim that the average spend is 82 based on the sample that we collected. The next tool we used for forecasting, and that's the only other that we're going to mention here, and it is a very, very widely used tool, is the principles of correlation and regression. So correlation is a statistical calculation that measures the strengths of linear relationship between two variables. Again, we take a sample, see how two values for two variables at the same point in time, or for the same company, for the same element of the population, see how they behave. And if they behave in a way that is related, that means they are correlated, some cases highly correlated. If they behave in a random way relative to each other, then they are not correlated. So correlation takes a value between -1 and 1, where -1 and 1 are perfect correlation, and 0 is no correlation. Now, the important thing as well is a correlation in 1 does not mean that they always change by the same amount, both variables. For example, if one moves by 1 unit and the other one moves by 1 unit, and that relationship always is present, the correlation is perfect of 1. But if one variable moves by 1 unit, and every time another moves by 2 units, or even by 10 units, it's also perfect correlation, because it's always 1, 10, 1, 10, 1, 10, and so on. That's perfectly fine. So say, for example, revenue is a function of price and quantity. So if I was to judge the correlation between number of units and revenue, it's going to be perfect. But if the price for the product is 10, every time I sell 1 more unit, revenue goes up by another £10. So it would be perfect correlation, but it's not the same amount that it moves. So correlation measures, as I said, the strengths of the linear relationship. But what it is just a number. 0, 0.5, minus 0.82. But you can't say, if this happens, this will happen to the other one. You just know that the correlation is there. The way to find a model that will provide an explanation and allows you to predict the value of one variable based on the other is regression. Because regression not just tells you there is a relationship, it tells you this is the model in which we can represent that relationship. Okay, so for example, every time you increase one variable by 1 unit, the other one will go up by 3.22 units. That's a model that you can predict, because then you say, if this variable takes this value, this one is expected to take that value. And so a regression model will look like this. What we have is we have 2 types of variables. We have a single variable y, which is the dependent or explained variable. And we have 1 or more variables x, which are the independent or explanatory variables. If we have a single variable, we have a simple regression model. If we have more than one, we have a multiple regression model. But in both cases, what they do is they allow us to predict the value of the dependent variable when as a function, of 1 or more independent variables. Now, if you look at that equation, each value of x represents the variable itself. Each beta represents a constant. Beta 0 is called the intercept of the model, which is if we make all the x's equal to 0, that is the value that I expect y to have. And then the other betas, beta 1, beta 2, etc., are called the slopes. And what they do is represent the number of units that you expect y to change when x changes by 1 unit. So for example, in that model, if x1 increases by 1 unit, y will increase by beta 1 units. There's an example coming up with actual numbers, and then we can see, and I'll go through that in there. And there it is. So this model is an example of a regression model where we are trying to predict the price of a car. And in this case, we are predicting the price of a car as a function of displacement, the year it was produced, the weight of the car, not the price of the car, the consumption of a car, the year it was produced, and the country. And what that gives us is to say that if no displacement, no year, no weight, and no country, which gives you an idea that a lot of times the intercept is a nonsensical number, then the consumption would be minus 313,886. But then the important are the coefficients. And the coefficients tell you that if displacement goes up by 1 unit, consumption goes down by 51. If year goes up by 1 unit, consumption goes down by 3,300, goes up by 3,322. If weight goes up by 1 unit, consumption goes up by 13.29. And if country goes up by 2,800 by 1 unit, consumption goes up by 2,871. So obviously you need to understand the variables. This is just to give you an idea of what those coefficients mean. Now, the important thing once we have these is now we have a model. So once we know the value of the displacement, the weight and the country where the car was made, we just put it in the respective values in the equation, and that gives us the value of y, the expected value of y. But we can only do that if the regression is a good model. It's a good regression. And for that, you look at 3 things. Number 1, you look at the adjusted R squared, which is at the top. That number, the higher it is, the better. The closer to 1 it is, the better. Because that is how much is explained by the regression. So in this case, those 4 variables explain 48% of the changes in the consumption of the car. That means that 52% is not explained. But in some cases, that's not bad, because there's a lot of different variables that affect a variable. So for example, here consumption is a function of how the driver drives, is a function of what type of fuel it uses. So there's a lot more variables we can think of that affect consumption. So developing a model with only 4 variables that explains 48% is not too bad. Then we look at the standard error, and the standard error, the greater it is, the worse, because that means that the data is more spread. And so even if the expected value is this, if the standard error is 0, that means it's absolutely bang on. The bigger it is, the more the data varies, and therefore the less certain we are of our outcome. Then we look at the significance f that you see in there, and the smaller that number is, the better. That case, you've got 0.00000019 zeros, 121, so it's quite a good value. And the final thing, and to a large extent the most important, because that's the one that if it's not met, the model is not useful, is the hypothesis testing. Remember I mentioned earlier regression is going to use hypothesis testing. We need to do a hypothesis testing on all coefficients, or each one individually, that they are significantly different from 0. Because if we can't be sure that they are, then the model is not good. So if, say, year has got a coefficient of 3,322, but if we made a confidence interval for that value, and it comes from minus 3,000 to 9,000, then it can be positive, but it can also be negative, and it can be 0. And what that means is, whenever year goes in one direction by 1, if I cannot be certain that the coefficient is different from 0, it means that the dependent variable, in this case consumption, can go up, but it can also go down. And that makes it useless as a predictor. And what we do here is use the principle of hypothesis testing we just saw. What do? We look at the confidence interval. You've got two columns there that says lower and upper. If 0 is not included, then we can be certain with 95% confidence that the coefficient is not 0. The next column is the p-value, and the p-value is the one we just saw a couple of slides ago. We compare that with a significance level of 5, and as long as the p-value is less than 0.05, then I can be 95% certain that the coefficient is not 0. And the next column, the t-stat, we compare with the t-critical. And because this is a large sample we used, the observations are 150, we can compare this with the z-critical. And the z-critical is plus or minus 196. So as long as the t-stats are outside of that range, which they all are, minus 315 is one extreme, 962, 677, 446, they're all bigger than 196 or smaller than minus 196. Again, all coefficients are significantly different from 0. That's very good. We've got a good regression. Okay, so in a nutshell, that's the output, and that's how we test the quality. Now we can use this model for prediction. Take any car, find the value for displacement, year, weight, and country, put it in the model, which you can see in the previous slide. So in this case, the beta 0 is the minus 313864. The beta 1 is minus 5167 multiplied by the value for displacement. Beta 2 is 3322.2 multiplied by the year of the car. Beta 3 is 13.29 multiplied by the weight of the car. And beta 4 in this case is 2871.67 multiplied by the country where the car comes from. So obviously the country in that case will have been given a number for each country of origin of the car. And that's how we use regression, and we can now predict, as I said, for any car that we want. Okay, so that concludes the first part, which is the forecasting. Oh no, there is one more element, a little detail between one and the other. One important thing for a business is to be able to manage their stock well. And so this is a slightly off topic from the previous forecasting, because the previous forecasting works for any variables that we are looking at, where we are trying to explain one variable as a function of others. Inventory forecasting is a little bit of between forecasting and optimization, because what we are actually going to be doing is find the level of inventory we want to order to minimize the cost. So in a business that sells products, we need to have inventory. We need to have stock to sell. But having the stock costs us money. Storing costs us money. Handling costs us money. Ordering costs us money. Everything involved with stock costs money, apart from the actual price of the stock. We're not referring here to the price of the stock. So if you go to a bicycle shop, obviously they buy the bicycles and they pay the supplier for the bicycles. But it costs them money, all the paperwork, the phone calls for ordering the bikes. It costs them money to transport the bikes from the supplier to their store. It costs them money because they had to rent the store or a warehouse where they have the bikes. It costs them money because some bikes may be stolen or damaged and they won't be able to sell them. So all of those things cost money. And so a lot of companies, and the more stock you have, obviously, the more expensive it is. So a lot of companies try to optimize their inventory management by minimizing those costs. They do that by understanding the following variables. Number one, how much demand do they expect for a period of time? Normally a year. Number two, how long does it take between the moment they place an order and the moment they receive the stock? Number three, what is the ordering cost? An ordering cost will include things like the placing an order, the documents, etc. Transportation. If the stock comes from abroad, any paperwork for the border controls and any taxes or duties that are due. And the holding cost, which includes the cost of storage, the cost of handling, any insurance potentially, any obsolescence, damage, theft, etc. And once you've understand those four things, you will determine what's called the economic order quantity. And the economic order quantity is how many units I should order each time I place an order. And the way to do that, again, I'm not going to demonstrate the model, but what we are doing is a balance between those two costs. The ordering costs are reduced if I place less orders. So if I have demand for a year, if on the 1st of January I place an order for every single unit I'm going to sell for the year, I only have an ordering cost once. That's the cheapest. But if I do that, I'm going to hold stock for a long, long time. So my holding cost is going to be very high. So from a holding cost perspective, the more orders I place, the better. Because the less units I'm going to have to spend money storing, handling, etc. So as I increase the order size, my ordering costs are going down. But as I increase the ordering size, my holding costs are going up. So the balance is to minimize the total, not to minimize one or the other. And you might know this because it's true if you look at the demonstration of the formula in any of the references books, you will find that the total cost is minimized when the ordering cost and the holding cost are the same. And that is calculated by using this formula. The formula is very simple. The quantity that I should order each time will be calculated as the square root of 2 times the ordering cost times the total demand divided by the carrying or holding cost. And the carrying or holding cost is the cost per unit per time period. So the average cost of holding 1 unit for 1 year. So that's the calculation. There's a long way to demonstrate it, but believe me, it is true. Believe me, it will be optimum, and you can then calculate when you determine the optimum quantity, you will find the cost, the carrying cost and the ordering cost for those, and the total, you will find they are exactly the same. So now let's look at ways to optimize. And the first one I'm going to mention is simulation. Now simulation, what we are doing, as the name says, is simulate. So we design a model that will allow us to forecast. Like regression, it is a model that will potentially have one or more independent or explanatory variables. But unlike regression, we will accept that the behavior of the variables is not linear. So regression is called linear regression because the relationship between the dependent variable and each independent variable is assumed to be linear. That's why we use the term slope. It's not the slope of a curve, it's the slope of a straight line. With simulation, what we are going to do is assume that input variables, independent variables, behave in different ways. And we're going to reflect that in the model, and the model is going to simulate various combinations of values for the various input variables and determine what the output is. So having a quick go through each of those bullet points, statistical analysis used to develop the model, maybe single independent variable or multiple, but always one single dependent variable. So sales is a function of price for a simple model, or sales is a function of price, advertising spend, and competitors' price. To generate a prediction, we assume a value for each of the input variables and determine the value of the output variable. And simulation does something, but instead of using a value, we define the way it behaves. And so our outcome is not going to be a single value like we get from regression, will be a range of values. So what are the steps that we do? Like everything, we start by determining what we believe is the model we are after. That is, what are the important variables? So if I want to impact my profit in a company, what are the input variables I need to manage? So it may include quantities, so sales quantity, sales price, cost per unit, spending on advertising, a number of different input variables. In this example, let's assume sales are a function of price, advertising, spending, and competitors' price. I will then collect data, a sample, for these variables and represent them graphically, each one separately. And what I'm going to do with that is what's in number 3, is to say, all right, I'm going to look at those scatter plots and say, how do these variables behave relative to the dependent variable? And they may behave as a normal. They may be continuous. They may behave like these. They may behave like these, whatever it is. We're going to see how they behave. And in so doing, we're going to determine something that we saw in the previous topic, which is a probability distribution that the behavior of the variable approximates. So maybe a Poisson, maybe a normal, maybe a triangular distribution, whatever it is. So once we do that, we're going to need some form of simulation software. And one possibility is to use AddRisk, which is a software that is available with that can be used with Excel. It's not part of Excel, but it uses Excel as a platform. And in that software, we're going to define those distributions. Once in step 4, we calculated the statistics. So for example, if you recall, for a binomial, we need the probability of success. We need to find that. For a normal, we need a mean and a standard deviation. For a triangular, for example, we need a minimum, a maximum, and the most likely value. For a uniform, we just need a minimum value. So whatever the statistics are for the distribution that we are going to use. Put that in the software, And with the software, we generate a range of values. So here, for example, is an output for example, profit. And so what that will tell you is, it will tell you a range of values, it will tell you the most likely values, and it will tell you a breakdown. What are, for example, here, there's 95% probability of getting more than 4.912, 95% probability of getting less than 5.838. And then you can see on the side, we've got a minimum, maximum, the mean value for the output variable, the mode, the median, etc. With that, we now have a range of values. So if we feel that we are happy with the output, that is, we are willing to accept the worst case scenarios, that's not going to kill us, for example, as a company, we can survive with those, and we really like the best scenarios, then we're happy we go along. If the output is such that it's a total disaster, then we're going to look, what do we do? And what we do in some cases, maybe stop producing whatever it is that in this case we were simulating. So it allows us to simulate up front and therefore make decisions that will avoid us being in a situation where something very wrong happens. The software then allows us to do other things like sensitivity analysis or optimization itself, where we find the optimum values, for example, that we should put on our input variables. For example, what should we charge? What should we spend in advertising in order to get the best results? Okay, so that is simulation. Key thing is determining upfront how we believe the input or independent variables behave. What shape do they normally take? Then we have optimization. Now, optimization is a very, very wide field. There are many ways of conducting optimization. In different fields of activity, there are different techniques that can be used. And I just wanted to raise your awareness to it, because in a lot of instances, that's what companies are trying to do. Not to say the majority of cases, is optimize the resources they have to get the best possible outcome. So in optimization, we determine the criteria that for us constitutes the optimum. So for most companies it will be profit, but in some cases it may be spreading a message. In some cases it may be generate awareness of a certain topic. In some cases, so charitable organizations, for example, will be to maximize the benefit they bring to whatever cause they are supporting. So there are other criteria that can be used, and based on that you will select the best element from a series of alternatives. So for example, airlines, what is the optimum for them in terms of flying a plane is to have 100% occupancy. But they know that some people buy tickets and don't show up. So they're going to overbook. But if they overbook by a lot, and a lot of people start turning up and not having a seat on the plane, that's going to cause problems. But if they overbook by a little, and every plane that takes off has got lots of empty seats, they have a problem. So the optimum will be determining how many seats they should overbook, sell over the capacity of the plane, to ensure that in most cases the plane is full, but no one is upset by not having a seat on the plane. Okay, so there will be an example of optimization. But as I said, in different fields there are different ways. There's lots of different approaches to optimization, depending on what it is that you're trying to optimize. So just be aware that in businesses, a lot of decisions will be about optimizing, because there's always, in most cases, going to be danger on both sides. So if I'm managing stock, for example, that we talked a minute ago, if I don't have enough stock, I don't spend a lot, but I'm going to have a lot of unhappy customers because they get to my store and say, I want these. Say, sorry, I don't have any more. Not only they will be unhappy, but they'll likely go to another store where they can buy. And next time they're not going to come to mine. They're going to go to the other. So I'm going to lose clients. I'm going to lose customers. But on the other hand, if I have too much stock and every day I don't sell the stock I have, it's going to cost me a lot of money. Imagine that stock is bottles of milk. If I keep ordering too many, I keep throwing away bottles of milk, and that's waste and that's costly. So I need to find an optimum where I try as much as possible to always have stock for my customers, but don't have too much stock left that goes to waste. That brings us, the optimization brings us to the last of the subtopics within this part 4, which is linear programming. There's a lot of situations in business where we have limitations on what we can do. And to be honest, there's most cases because we can't just sell however many units we want. So that's a clear limitation. In other cases, we may have limitations on access to raw materials, access to certain type of expertise that we require in our business. So there's a lot of other limitations, a lot of resources that are scarce. And a lot of times we have conflicting claims on those resources. Say, for example, a consultancy firm that has 5 tax consultants. They potentially have 15, 20, 30 clients who want to use that expertise. And so they have to decide how they're going to allocate the time of each of those tax experts to the different clients. And that's an example of service, similar, and can use exactly the same type of analysis and the same modeling that product-related companies can. So one example here of a situation like that, where we have scarce resources, conflicting claims on those resources, and in situations like these, also very frequent, we have a linear relationship. So take the tax consultants, they work 40 hours a week, and every time we put 1 hour to one client, we take it away from another client. Take the example here, we are making different energy bars, and they both use 2 ingredients, and every time we make one of one, we take ingredient away from the other one. So here, for example, to make an ACE bar, we need 10 grams of ingredient 1. So if we use those 10 grams, we don't have those 10 grams for spades, which would make 1 bar with 8 grams and a quarter of another bar. So the relationship in that case is linear. So the example we've got here, and there is an Excel file that goes through these in detail, so feel free to check it as well. And you'll see the formulation there, which is in the next 3 slides as well. We've got 2 ingredients, as I said, 2 different products that we make, bars, aces, and spades, and we have limitations. And the limitations, the constraints are on the quantity of ingredient we can access, both ingredients, and are also of the size of the market. So in all cases, maximum access that we have and maximum sales that we can generate. So the problem we have is, how do we allocate the resources to make sure we make as many bars that the market wants to buy as possible? So not make 1,500 aces and no spades, because we're only going to sell 1,000 aces anyway. And we're going to do that in a way that maximizes what's important for us, which in this case would be profit. So we got 50p is the profit for each ace and 70p for each spade. So we do Excel and we represent the problem. What we have here in the black boxes, that we have the data, the unchangeable values. So the ingredients, the quantities of ingredients we use for each bar, 10, 8, 6, 14, and the profits that we make on each bar, and also the maximum availability of demand, maximum sales, and available for ingredient. Then in the blue box, we have the unknown quantity to start with, which is the optimum. And that's what we're going to ask Excel to give to us. We could do it manually, but we're going to have to keep trying and trying different options. Excel, because it can operate quicker than our brain and our hands can look at various different combinations of production of A and S and give us the optimum combination for our production. And then we have one cell, which in this case is the profit cell in the third column, that tells us what is that we are trying to maximize. And in that case, what we're going to do next is tell Excel to do it for us. And Excel does it by using something called Solver. And you can see that dialog box says Solver parameters. Now Solver is an add-in to Excel, which is not necessarily always available, always visible, but is always available. Now, if you don't have it when you open Excel, the way to do it, and I'll do it very quickly, is go to press on File on the left-hand side of the options, scroll down to Options, scroll down to Add-ins, and then select the add-ins that we want, which in this case is Solver. Now, sometimes it's not easy to do, and if I was in a classroom, I could show it to you. Here is not as easy, and rather than waste the time with that, I'll just give you a recommendation. Go online to Google or anything and just type in how to access Solver on Excel. I've tried it. You get it straight away, and it's a lot easier than having to keep coming back here and watch this video whenever you need it. So just type in how to access Solver on Excel and you'll see it. So Solver dialog box asks us for those three things that I mentioned. 1, what is our objective? 2, what are the cells you want me to change? What are the recommendations you want me to make? And 3, what are the constraints? So the maximum sales and the maximum availability. You can see all of that now in full detail in this slide, where we've got the dialog box with Solver, and you've got in there set objective, where we've got cell D18, which is where the calculation of the profit is. And if you look at the previous slide, you will see that that's a formula that you have in that cell. Then you've got, by changing the variable cells, and you got B9 and C9, which are the cells with the production levels that we want Excel to recommend to us. And you see in the previous slide, I had put in there the number 1. Just, I could leave it blank, or you can put any number that you want, and Excel will override those numbers with the numbers that it recommends, with the optimum solution that it has come up with. And then you've got the constraints. And the constraints, you can put numbers in the constraints, but I very strongly urge you never to do that, because you're going to need to understand the model. You're going to need to define the model on Excel, and therefore never do that. Always use cells from Excel. You can do cell by cell for the constraint, or you can use range as long as those ranges are well organized. So here we've got the constraints on inputs, where you've got there B14, B15, which are the cells that at the moment have got 16 and 18,000, less or equal than D14, D15. So Excel treats them in the same order. So you've got B14 compares with D14, B15 compares with D15, and ensures that in the ones on the left hand side, you've got no more than the maximum available of each of the ingredients. Then you also have the constraints for the market. So you've got B9 and C9, which are the ones that it is calculated. They can't be more than the maximum demand available for our products. So in this case, less than B11 and C11. Again, it takes the same order. So Excel takes into consideration those constraints that we tell them, and calculates the values in the changing cells to maximize the objective. Notice just underneath the row set objective, you've got 2, and you can select maximum, minimum, or you can try to achieve a certain value, if that's the case. In this case, because it's profit, we're trying to maximize, so we tick that box. There is also another little box in there that says make unconstrained variables non-negative. It's very important to click on that one, because a lot of times the solution may be that we make a lot of one particular product and we use resources from the other. But if we don't tick there, we may, or Excel may give us a solution which is make infinite negative numbers of one product and make infinite positive numbers of another. And obviously that's nonsensical, because we can't unmake products, or we can't unsell products, or any of those things. So the constraint, making unconstrained variables non-negative, it means that on those cells B9 and C9, Excel knows that it can't put negative values. And so once we've defined the model, we click on solve, and solve gives us the optimum. And what you see here is that Excel is using the full available quantities of ingredient 1, and Excel is selling the maximum demand for stars. But there is some slack on ingredient 2, because we're only using 18,000 and 20, and when there's available 20,000, and the same for demand of aces, where we're only selling 800, but the maximum sales is 1,000. So you may ask, but then I could sell some more aces. Yes, but to sell some more aces, you would need to use more ingredient 1. And by doing that, you would have to take it away from spades, because you don't have any more 1. So Excel has taken that into consideration. And what it did, if you look at it, stars use more ingredient 2, but less ingredient 1. But what's constraining us the most is ingredient 1. So we are better off selling more of the product that uses less of the resource that we have less, and it gives us a higher profit because it gives us 70p versus 50p per bar. So Excel has taken that into consideration, has tried all possible combinations of production, and has determined the maximum. So if you want to challenge Excel, feel free, try to find a combination that is better, and you won't, because Excel has optimized. And so that's linear programming. That's how Excel does it, and it's one other element of optimization. And that concludes this topic. So all that's left for me to say is there are some references. As I said, for those of you, especially those for whom these topics of estimation and regression and correlation and optimization are new, make sure you go through some of those resources, some of those references. Thank you for your attention. Don't forget you also have the exercises which have the solutions, and practice.